All right, boys and girls, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Stop by the deli. Get yourself some General Tso's for order out day. Oh, it was great. And an egg roll. All right, this is the hardest theorem of the year so far, and it's 4-4, the equidistance theorems. I know from experience that this is going to separate a lot of the people in this class. So, you got to stick with this one. You might have to watch this video twice. All right, so let's think about it. What does it mean to be equidistant? Okay, that's something I want you to think about right now for a second. So what if you said you sat equidistant from both exits, let's say like at a movie theater or at a restaurant? Well, here, if this is exit 1 and this is exit 2, where could you be seating? Well, a lot of people interpret equidistant as a midpoint. Well, that's one possible spot you could be. So you could be there. There, the red dot is the same distance from exit 2 as it is from exit 3. But you could also be right here. If you think about it, if I connected this red dot and I connected this red dot with that triangle appears to be isosceles. Okay, if you could imagine a segment drawn between the blue lines. Well, I think you could also be here. But you could also be here. Okay? So to be equidistant would mean that you are the same distance from both points. So what if you lived equidistant from Jersey Mike's and Subway? You'd go to Jersey Mike's every time. Every single time. Unless you needed to go to the bathroom, and then maybe you'd go to Subway and use their bathroom. All right, moving on. So, how do we determine distance? This is something you've never probably thought about. The answer is relatively obvious, but not to everybody. What if I said, how far is point A from line X? Is it that far? Or is it that far? Or is it that far? It's not. None of those are right. It's that far. This is why your doctor tells you to stand up straight. You don't really get that, but when your doctor tells you to stand up straight, it's just his way of saying, please form a perpendicular with the ground so I can measure your height. If you could amazingly stand up on both feet but not be straight, so if somehow you were able to stand up because you were crazily balanced, like this. Well, that doesn't look like what I'm trying to describe. If you could stand up like that, then your doctor would tell you you were 3 feet tall. This is why your doctor tells you, if you think about that, to stand up straight. They want you to make a right angle with the floor because the distance between the top of your head and the floor is what they're measuring. Okay? So, how do we determine distance? It is the shortest possible path between two geometric objects. Oops. And as it turns out, if you think about this example now, the shortest path between a point and a line is the path that forms a right angle with that line. So that is how we measure distance. Okay, so remember that. All right, so now we have another day to review the perpendicular bisector theorem. Some of you are probably like, we just did this last section. Why is he including this again? Because other of you are like, what's a perpendicular bisector? Okay, so we have to know this. If we don't understand what a perpendicular bisector is, then there's no way we'll understand the equidistance theorem. Okay? So a perpendicular bisector is a line, a ray, or a segment that bisects another segment and is perpendicular to that segment. So to review, if I had this black segment and I wanted to bisect it with a perpendicular bisector, let's say with a line, I could say, if we knew both of those pieces of information to be true, I could say that that blue line was the perpendicular bisector of the black segment. Following along? I hope, because it hasn't gotten hard until now. Here we go. So, this is a theorem that we do not have a name for. So you cannot call it the equidistance theorem because there are two of them, and they're vastly different. Okay, one of them is actually the converse of the other one. And I'm going to make you write this out because writing it out over and over again will help you actually learn the theorem. Okay, so you're going to be annoyed by me, and I can... Oh, I went from endopints to endpints. Oh, no. Let's go with endpoints. I just want to get this right so I don't confuse you guys. Okay, that's better. So, here's the theorem. It says, if 2 points, you can see I've got 3 different pictures here, and all the pictures you can see 2 blue points. If 2 points are equidistant from the endpoints of a segment, then those 2 points determine, we'll talk about what that means, the perpendicular bisector of that segment. Okay, so what I'm saying to you is that this point is equidistant from the endpoints of a segment. That means that those 2 red segments are congruent. This point right here is also equidistant from the endpoints of that segment. So that means that red triangle and that green triangle are both isosceles triangles. Excuse me. So if that is true, then the blue points determine the perpendicular bisector. What that means is that the blue points, if you connected them, contain a line, and that line is the perpendicular bisector of the black line. So I'm going to draw these out. I'm going to draw the examples kind of the same in each one. Here, that blue point is equidistant from the endpoints of the black line. That blue point is equidistant, okay? And therefore, those 2 points determine the perpendicular bisector line of the black line. So now we know. Okay, we know that to be true now. And then finally, I've got the red. These red lines are congruent. These green lines are congruent. And therefore, this blue line must be the perpendicular bisector. Now, I failed to make this perpendicular, so let me fix that. All right, so in our class, we're going to refer to these as the 3 different types of perpendicular bisector problems. This, to me, looks like a kite. So that is the kite example. Okay, this one here, this is your your isosceles triangle example. In this case, one of the 2 points that determine the perpendicular bisector is actually the midpoint of the line that we're trying to bisect. Okay? And then the third type of situation where we use this, I refer to as the Star Trek example. I can proudly say I've never seen Star Trek, and I probably just offended some of your parents, but I do know what Star Trek looks like, and this right here is like the Star Trek sign, I think. Can anyone confirm that? Okay? So we will call this as the Star Trek. Okay, or you could also maybe refer to it as the stealth bomber. Okay, I'm just describing what the pictures look like, because what you're going to have to do is, hopefully you will see a picture like this, like next week, and you'll be like, oh, this is a perpendicular bisector problem. Or if it looks like this. All right, stay with me, you're doing good. Now, this is the second equidistance theorem. If a point is on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of a segment. So what we have here is we know that the red line is the perpendicular bisector of the black line. That's given to you. So it is given to you that the red line is the perpendicular bisector. Well, what that means is that any point on that red line is what? Is equidistant from the endpoints of the black segment. Okay, let me switch this over to line tools real quick. All right, so here, let's do that again. So this black line, or this green line, they're equidistant to each other. And what if I chose a point up here? Well, it would still work. Any point on that line is going to produce two segments that are equidistant from the endpoints of the segment. What about down here? It still works. Okay? So look, this is kind of a long video, and I encourage some of you to go watch it again. Rather than do an example in this video and make it really long, we will kick off class with a warm-up, and that warm-up is going to be a proof involving the equidistance theorems. Hope everyone has a wonderful weekend. Boom!